Hello, prob stats, and welcome to 10.4. This is multiple regression, and this is getting a little bit more realistic. Instead of one variable, we can have multiple variables, 3 or 4 things that actually contribute to how our data is represented. So you're going to need stat disk again. Make sure you have your notes out, and let's go. All right, the objectives this time are to determine, here we go. We're going to, from technology, determine whether a multiple regression equation is suitable for making a prediction. So should I use multiple variables, or is one variable better predictor? Okay, we're going to look at different combinations of predictor variables and identify the combination that results in the best multiple regression equation. All right, a multiple regression equation just means there's more than one x. So there's many different variables. All right, this is from a sample. And it is the same thing as it is for a population. We just has many different x's, and they represent each other. Okay, y hat is a predicted value of y. So when we do it for a sample, it should do the same thing for a population, which we like. K is the number of predictor variables. So how many things am I going to use to determine my value of y? N is the sample size again. Requirements. We have to have a specific set of x values, so it has to be specific. It can't be random. The regression equation is associated with random error, often denoted by epsilon. So random error is epsilon, is what you'll see there. Such errors are normally distributed with a mean of 0 and a standard deviation. The random errors are independent of each other, which we'll talk about a little bit, not a lot. Okay, we're going to use data set 1. On our body data. So when you go to your, let's get over here to statistics. Let's make sure we're in the right place here. Make sure you go to data sets, elementary, and the body data. So this is the data you want up that we're working with. Okay, I want to look height, waist centimeter, and weight for a sample of 153 males is what we're looking at. So I want to know, I'm going to do a multiple regression equation with reasonable variables is the weight of the male. So what predicts the weight of a male? And I think it's height and waist circumference. So we're going to look at these two and see what we come up with. All right, so now when you're in stat disk, so let's get back over here. We're going to go to analysis and multiple regression. All right, now the things I want to do is I'm going to look at, I want to find weight, and I'm going to look at height and waist. The dependent variable is what we're trying to find. So when you look at the dependent variable, that's my weight. So weight is what I want to calculate. So make sure you got all those clicked correctly and hit evaluate. So now when we look at this evaluation, if you look, the coefficients are very similar to our line that we have. The b sub 0 is our intercept. The b2 and the b3 go with our variables. So this actually goes to the height and the waist. All right, so let's go back and write this equation, then we'll come back to stat disk and look at this some more. So now that we have everything, here's the variables that we're looking at, right? So now to write this, the 124, I'm just going to round to the nearest pound. Negative 124 is where we're starting. The first one goes to the first variable that we clicked, which was height. So the 0.608 goes to the height. It just goes in order. This is this on my thing. 1.04 now goes to the next variable, which was the waist. So we just write those out. And this is my prediction equation for more than one variable. Now, let's look to see if it's any good or not. Is a multiple coefficient of r squared modified to account for the number of variables and sample size? It's found using stat disk on our output. So if you look up here, we have an adjusted r squared. And this is kind of where we're looking at. We have a regular coefficient of r squared and our adjusted r squared. We're going to use common sense to see if this makes sense. We're going to look at our p-value to see if it works well. Then we're going to consider equations with high values of r squared. So if this is high, we like it. If it's low, we're not so happy. So the 0.88 is high, and that's good. We thoroughly like that number. Okay, instead of including almost every available variable, we want to include as few as possible, because the less variables, the less room for error. So when we go through here, we want to try to include relatively few predictor variables if we can. Okay, select an equation having a value of adjusted r squared with the properties. The variable is included. The value of the adjusted r squared does not increase very much. So if we include the variable and this does not increase, we don't need it. For a particular number of variables, select the equation with the largest r squared. So we always want the largest r squared. So if we do 2 or 3 different things, we look at those. In excluding a predictor variable that don't have much an effect, so if we put one in and it doesn't change it much, we do not use it. So you exclude a predictor if it does not have much an effect on the r value. If 2 predictors' values are very high linear correlation coefficients, there's no need to include both of them. So if they both give me the same answer, we only use one. Okay? We need the one that we can exclude the lower value because we always want the higher. But if they're relatively the same, no reason to have both. That's too much work. All right. So we're looking at Appendix D. We're going to look at foot and height in Appendix D, including the ages of foot length, shoe print size, shoe size, and height for each of our variables. So I lied to you a little bit there. Okay, let's go back to our data. We're going to go to data sets, and we're going to body data. This is what we're looking at. All right, let's go back. Now, we look at our predictors, and if we put in age only, we get an R value of, let's show you what that's doing. So if I go up here, and I go to analysis, and I only look at age and weight. And then I click on weight, and I hit evaluate. Oh, it doesn't like it because there's not enough of them, because this is truly a linear sample correlation regression. We're going to look at age and weight, evaluate. So let's go down here. Our adjusted r squared, is a negative 0.00332. Our r squared is 0.004. Hang on. Sorry about that. I had the wrong data set. This here is supposed to be data set 2, foot and height. So please change to data set 2. Go to your correlation coefficient, because we're only going to do one at a time here now. So I know the height versus the age. So when you do that, and you scroll down, your r squared is 0.1772. And then we do that again for foot length and shoe print, all from here. But now, when I want to do the double ones, I have to go to multiple regression. So go to analysis, multiple regression, and we're going to look at foot length and shoe print. So foot length, shoe print, height, and height is the one I want to evaluate. So when we look at those two together, we have an r squared of 0.7485, which is nice. Now let's look at age, all of them. Not sex, I don't think. So age, shoe size, foot length, there we go. Evaluate, and we have an adjusted R 0.7549. Now, I know that this one is the best, but is the difference large enough to overcome everything else? So we look at age, and that's 0.172. That's really low. So we know this is bad. Whoops. So we cross him off. We don't like him. Now between foot length and shoe print, the foot length is better. Shoe print is probably more practical, because if you had a crime scene, I'm pretty sure they're not going to be barefoot. But for the statistics rule, we'll go with foot length. So foot length is here is better than shoe print length. So that's gone. Now, let's look at these guys. If I do the foot length and the shoe print length, it is larger than this, but by only 0.04. That's only 0.04 better. That's not enough for me to include 2 variables. When you do all 3, this is absolutely the best, but it's by only 0.05 better than this one. That's also not enough for me to include that many variables to calculate my thing. So this time, a multiple regression is not okay. We want to do a single regression, just a y equals x line, because it gives us a better value. All right, I hope you did okay with those. Now, the other critical thinking is, truly, would we use the footprint's length? Probably not. We would use the shoe size length, because the shoe size length is what I'm going to get at a crime scene. So that would be a better practical value. Okay? So we go here. Our height would be the 64.1 plus a 4.29. This came from our stat disk when we plugged it in, and we got of our foot length. If I did the shoe print length, which would be more practical, you would use this into your stat disk again underneath your regression coefficient, or your regression, and we'd have 80.9 and 3.22. And it would only be a single. All right, now I would like you to use the body data, and I want you to figure out which one is best. All right, pause and try yours. Okay, if you did all the combinations, you would have done height, waist, arm, height and waist, height and arm, height, waist, and arm. So height was 1.2. Okay, obviously that's bad. Okay, waist was 0.79. That was good. And arm was 0.78. All right, out of these two, waist is good. Now we look here, 0.83 is only 0.04 better than 79, so this is not enough more to make me go to height and waist. 0.88, okay, that's almost a full percentage. All right, for this, I would go. So this would be no, and now I go to height and arm. 0.94 and 0.88 is 0.06 again. So this is a little bit in between. You could choose yes or no. You could go with waist and arm or height, waist, and arm. I'm going to do this one just to show you how to write that equation, so you make sure you get it right. But both of these would be better. I would probably almost say this is the better of the two. So now let's go to stat disk. And since we're going to use a multiple regression this time, it was better than our lines. Instead of a regression, correlation, and regression, we're going to do multiple regression. We're going to do weight, height, waist, and arm. And we're going to calculate someone's weight and evaluate. All right, so when we look at these, we have our numbers at the top here. So we have the negative 124, the 0.5136 goes to the height, because that's our first one. The 0.663 goes to the waist, and the arm circumference is 1.625. So if we use all of those, your equation would be, what's down here at the bottom of the page, right here. All right, now if you decided to do the waist and the arm, which is probably the better bet, we would use waist and arm, so we would get rid of the height. Now when we evaluate, we'd have a negative 43 for our intercept, 0.61 would go to the waist, and 1.95 would go to the arm, and you would create your equation. I hope you did well. All right, now let's look at our p-value. Our p-value down here is 0, 0, 0. So yes, p-value is 0. This is good. So we have a great equation to represent our weight using height, waist, and arm. Actually, it would be the same for your height, or your waist and your arm. So I'd probably still go with that one. All right. So now let's look at these dummy variables. Okay, what a dummy variable does is it actually replaces values like 0 and 1 and to represent different categories. They're qualitative data, so we don't do math with them. They're just representation to make our life a little bit easier. We use these a lot for male, female, like when we do heads, tails, we would use 0, 1, things like that. It's called the dichotomous variable. It's used because it's not actually any quantitative value. All right, it's qualitative. We do not do any math with it. Okay, the table below, we have family heights. It's from data set 5. So we're going to use 0 for female and 1 for male. Those are our dummy variables. Okay, it's given that a father is 69 inches tall and a mom is 63 inches tall. We want to find our regression equation to predict the height of a daughter and a son. So to do this, this is our data that you would have. You would have downloaded that into StatDisk. We're going to use multiple regression from part 1. And we're going to use our regression coefficient of the height of the father and the height of the mother. All right, and the sex. So our dummy variable has to deal with the sex, where the value of the dummy variable is either 0 for a daughter or 1 for a son. So that way it tells if I need to add that 6 inches or not add that 6 inches. Because for a daughter, they're usually shorter, so the 0 goes in here. All right, and for a son, the 1 would go in there, so I would add the 6. So it gives us one equation instead of 2, making life a little bit easier. Oh, we already talked about that. I hope you don't have any questions. All right, I would like you to pause and use your dataset body type, create the regression equation to predict the height of a person using their gender, height, and waist. All right, pause and try this. All right, I hope you type this in. We got a negative 137, so this is where we're starting our thing at. We have a negative 2.69, which is going to go to the gender. We're going to have a 0.699, which is going to go toward your height, and a 1.04, which is your waist. So now, when you wrote your equation, you should have the weight is equal to a negative 137 minus 2.69 times gender plus 0.699 for your height plus 1.04 for your waist. So according to this, if you're a girl, if you're a boy, we're going to subtract 2.69. And if you're a girl, this is going to go away and we're going to leave it as is. All right, I hope you did well. Good luck with your homework. You're doing 13 and 15. Post questions if you have any.